All right, here are the answers to homework 9. I'll scroll through them pretty quickly, then I will explain them all. Pause as you need to. Here we go. Okay, so let me start on the first one, and I'll explain each one. Here we are trying to write an equivalent expression with the lowest base possible. So all of these need to be a perfect square or perfect cube if you're going to rewrite it with a lower base. It turns out that 9 is a perfect square, so 9 can be rewritten as 3 squared. But since the 9 was to the 6th power, the 3 squared must be to the 6th power. And so my final result is 3 to the 12th when I do the power to a power rule. Here I can only rewrite it with a lower base if the base is a perfect square or perfect cube. And 8 is a perfect cube. It is equal to 2 cubed. Of course, the 8 had an exponent on it, so that exponent needs to go on the 2 cubed also. And then when I do the power to a power rule, when I multiply them together, this simplifies to be 2 to the 24th. 49 is also a perfect square, so 49 can be rewritten with a lower base. 49 is equal to 7 squared. Of course, the 49 had an exponent on it, so that exponent needs to go on the 7 squared also. And then when you simplify this by using the power to a power property, meaning you multiply the exponents together, you get 7 to the 10th power. And number 4, again, you can only rewrite this with a lower base if the base is a perfect square or perfect cube. 125 is a perfect cube. It is equal to 5 cubed. So I have rewritten 125 as 5 cubed, but the 125 had an exponent on it, so the 5 cubed has to have the same exponent. And then when you use the power to a power property, that means you can multiply the powers together, your final result is 5 to the 21st. Number 5, okay, we want to try to simplify both sides. If I can lower the base, I will lower the base. If not, I'll just simplify it using an exponent property. In problem 5, the bases cannot be lowered because they are not perfect squares or perfect cubes. All you can do is use the exponent property. On the right, you have a power to a power, so you can multiply those together. On the left, there's nothing to simplify. And the final result here is, which one is bigger? Well, you need to remember that when you multiply fractions together, every time you multiply by a fraction, it gets smaller and smaller and smaller. The more times you multiply by a fraction, the smaller it gets. So actually, 1/5 to the 17th is bigger than 1/5 to the 18th because it has been multiplied less times. In number 6, I see I do have some perfect squares and cubes, so I can lower the base. 9 is a perfect square. I can rewrite it as 3 squared, and it is to the 13th power. Then I do the power to a power property, and I get 3 to the 26th. 27 is a perfect cube. It can be rewritten as 3 cubed. But since it was to the 9th power, this would be to the 9th power. And then when I do the power to a power property, I would multiply those together and get 3 to the 27th. And of course, 3 to the 27th is greater than 3 to the 26th. Number 7 is probably the hardest problem of these. All of these can have their base lowered because all of these are perfect squares or perfect cubes. Let's start with the fraction on the left. 8 is a perfect cube. It's equal to 2 cubed. Of course, the 8 was to the 15th power, so the 2 cubed is to the 15th power. And so my numerator here is actually 2 to the 45th power. 2 to the 10th cannot be lowered because 2 is not a perfect square or perfect cube. And now, this fraction can be simplified because I have the same base on the top and bottom. And when you are simplifying a fraction or dividing, what do you do with the exponents? Well, you subtract, of course. So this would end up being 2 to the 35th power. Let's go to the right. 16 is a perfect square. So 16 can be rewritten as 4 squared. But the 16 was to the 9th power, so this would be 4 squared to the 9th power. And then when you use your power to a power rule, it would be 4 to the 18th. The problem is, that thing can be reduced again, because 4 is still a perfect square. So the 4 can be rewritten again as 2 squared. Now the 4 was to the 18th power, so the 2 squared is to the 18th power. And then finally, when I do the power to a power rule, I get 2 to the 36th power. And finally, 2 to the 36th is greater than 2 to the 35th. All right, number 8. Number 8, I cannot reduce the base because the base is not a perfect square or perfect cube. So I'm just going to keep the base, and in fact on the left, there's nothing to do. On the right, I have 12 to the 2nd to the 3rd. So I can do the power to a power rule and multiply those together. And then it turns out that 12 to the 6th and 12 to the 6th are of course equal to each other. Number 9, I do have a perfect square for the base, so I can lower the base. 25 can be rewritten as 5 to the 2nd power. Of course, this was to the 8th power, so 5 to the 2nd needs to be to the 8th power. And then finally, I can use the power to a power rule, multiply those together, and get 5 to the 16th. Right? 125 is a perfect cube, so it can be rewritten as 5 cubed. Of course, the 125 had an exponent on it, so the 5 cubed needs to have the same exponent. And then finally, when you do the power to a power rule, you can multiply those exponents together and get 5 to the 15th. And finally, 5 to the 16th is greater than 5 to the 15th. Number 10, both of these bases are perfect squares or perfect cubes, so they can be reduced. 27 is a perfect cube. It is equal to 3 to the 3rd power. Of course, the 27 had an exponent of 12, so the 3 to the 3rd needs an exponent of 12. And when you simplify that by using the power to a power rule, that means multiplying those together, you get 3 to the 36th. On the right side, 9 is a perfect square. So 9 can be rewritten as 3. Wow. You know what? I wouldn't do that first. I guess the first thing I would do is I'd do the power to a power rule and get 9 to the 18th. This will save me work. Now 9 is a perfect square, so 9 can be rewritten as 3 to the second power. Of course, the 9 had an exponent on it, so the 3 to the second power also needs the exponent. And finally, when you simplify this, using the power to a power rule, where you multiply those together, you get 3 to the 36th. And it turns out that these are equal to each other. All right, now we have some basic exponent problems. Here we are multiplying, number 11, we are multiplying these together. When you multiply the coefficients. 2 times 7 is 14, but you add the exponents. When you're multiplying, you add the exponents. -2 plus 5 would be 3. In number 12, it's another multiplying problem, so I'm going to multiply the two coefficients. -3 times 6 is -18, but I'm going to add the exponents. I have 5x's here, I have 1x here, so 5x's and 1x makes 6x's multiplied together. In the next section, I am using the power to a power rule. Here, I have x to the 6th to the 5th. The power to a power rule says I can multiply those together and get x to the 30th. In number 14, my exponent that's on the parenthesis needs applied to each term in the parentheses. This would give me 2 to the 3rd power, x to the 3rd to the 3rd power, and y to the 5th to the 3rd power. So I have applied this 3 to each thing in parentheses. And now let's simplify that. 2 to the 3rd power is 8. When I have a power to a power, I multiply them together and get 9. And again, when I have a power to a power, I multiply them together and get 15. Last step with number 15 here, I made a mistake on this problem. I forgot to put the parentheses in. It should have looked like this. If you corrected my mistake and put parentheses in, you would then apply this 2 to each thing in parentheses, giving you 3 to the 2nd, x to the 3rd to the 2nd, over 4 to the 2nd. And then when we simplify that, we get 9, because 3 to the 2nd is 9. Here we have x to the 3rd to the 2nd. We would simplify that by using the power to a power rule, where we multiply them and get x to the 6th. And on the bottom, 4 to the 2nd power is 16. In problem number 16, we are dividing. And when you divide, you subtract or cross out the exponents, or the bases. I have 20 11s on top, and I have 7 on the bottom. So if I subtract the exponents, I would get 11 to the 13th power. Here I have a little more complicated fraction. I can't just subtract. I need to first reduce the coefficients, 8 over 10. You're either reducing that on your calculator, or you're figuring out by finding a number that goes into both 8 and 10. In this case, they can both be divided by 2. 2 goes into 8 4 times, and 2 goes into 10 5 times. Then we take each variable separately, and we cancel out the common variables. I have 2 m's on top, and I have 1 m on the bottom. So when I go to cancel that out, I would be left with 1 m on top. Right? You're always going to end up with a variable either on top or bottom, wherever there's more of them. With the n's, I have more n's on the bottom. Right? So I'm going to end up with n's on the bottom. The only question is how many. And because there are 3 more n's on the bottom than there are on top, I end up with 3 n's on the bottom. And last up, the p's. There are more p's on top, so I'm going to end up with p's on top. And because there's 5 on top and only 3 on the bottom, that's 2 extra p's on top. And finally, the negative exponents. Remember, when you have a negative exponent, it means take the reciprocal. In number 18, I need to take the reciprocal of the x. Taking the reciprocal just means moving that term to the opposite place in the fraction. So the x needs to move to the bottom. By the way, notice how I made this into a fraction by putting it over 1, since it was not a fraction already. And I'm going to move the x's to the bottom, giving me the 3 on top, but the x to the 7th on the bottom. In number 19, since I just have a single term, I'm not going to make it a fraction. I'm just going to take the reciprocal. The reciprocal of 2 is 1/2. So I guess I did make it a fraction, actually. But by taking the reciprocal of the 2, that turns the exponent positive, and my final result is 1 over 2 to the 4th. And I could leave it like that, or I could go ahead and simplify 2 to the 4th and make it 1 over 16. In section 5, we know that an exponent of 0 means the answer is always 1. Anything to the 0 power equals 1. So 11 to the 0 power equals 1. 49x to the 0 power actually equals 49, because this is actually 49 times x to the 0. And so it's 49 times 1, because anything to the 0 equals 1, and that's why the answer is 49. Finally, I have 3 problems which are somewhat difficult, mixed problems. In number 22, I have a big fraction to reduce. But I also have some negative exponents to take care of there. Let's go ahead and do this step by step. So first, I would reduce the coefficients, 12 over 18. Either type it into your calculator and have your calculator reduce it, or you could figure out that both of those can be divided by 6. 6 goes into 12 twice, and 6 goes into 18 3 times. Now let's start handling the variables. The x's have 4 x's on top, and they have 1 x on the bottom, right? So when I go to cancel out the x's, I can only cancel out 1, and I'm left with 3 x's on top. Remember, you're always going to have variables left over in the place where there's more of them. Since there were more x's on top, you end up with x's on top. Next up is the y's. The y's are tricky because the y's have a -5 on top and a -3 on the bottom. Because each one has a negative exponent, that means you need to take the reciprocal or switch places in the fraction. So the ones that are on top go to the bottom, and the ones that are on the bottom go to the top. Now you're ready to reduce. And since there's more of them on the bottom, you're going to end up with y's on the bottom. The only question is how many. And because there's 5 on the bottom and only 3 on top, that's 2 extra on the bottom. So your final result has 2 y's on the bottom. Last up is the z's. The z's have a negative exponent on the bottom. So those need to move to the top. But the ones that are on top are staying there because they have a positive exponent. So now all your z's are on top. You just need to know how many. There were 7 up there to start with, and you just moved 2 more up there, giving you 9 z's on top. And we're done with that one. Number 23 requires 2 steps. First, we've got to take care of this first term that has an exponent on it. Once we get done with that, we need to multiply it times the second term. All right, so first, let's do the exponent on the first term. I would apply the 2 to the 3, and I would apply it to the x to the 5th. When I simplify those, 3 to the second power is 9, and x to the 5th to the second is x to the 10th. I have now simplified the first term, and I am ready to multiply it by the second term, 5x to the 4th y. When you multiply those, of course, you multiply the coefficients. 9 times 5 gives you 45, but you add the exponents when you're multiplying terms. I have 10 x's in the first term and 4 x's in the second term. That's 14 x's. I have no y's in the first term and 1 y in the second term, so that's a total of 1 y. And there's my result. Number 24 requires maybe 2 steps. It certainly requires you to multiply these two things and multiply these two things. So hopefully you're getting good at multiplying at this point. You multiply the coefficients. 3 times 4 is 12. You add the exponents. 2x's and 3x's is 5x's multiplied together. All right, over here I'm multiplying the coefficients. 2 times 5 is 10. And I'm adding the exponents. 5x's and 2x's is a total of 7x's multiplied together. And then the last thing you would do is you might add these together if they're like terms. But in this case, they're not like terms. The first one has an x to the 5th, and the second one has an x to the 7th. So since they do not have the same variable and exponent, they're not like terms, and they cannot be added together. And this is your final result. All right, hope that helps.